In this video, we will talk a little bit more about how to construct finite difference method by using the standard Taylor approach. Now, the example that I use here is the trapezoidal method, and the reason why I use this method is because in the book, the trapezoidal method is constructed by using numerical quadrature, which means that we derive a finite difference approximation by integrating the differential equation and then using a numerical integration scheme instead. Now, that means that the book does not derive the trapezoidal method using a Taylor approach, and just for the fun of it, let's try to do that together also so that we can achieve a deeper understanding of how the whole Taylor approximation thing works together with the construction of finite difference methods. So here I have written up the trapezoidal method as it is introduced on page 16 in table 1.3. I have this thing here, which just to gain an understanding of what we are working with, we can try to play a little bit around with how this equation looks. So this equation is equivalently also yj plus 1 minus yj equals to k halves times the approximation of y prime in tj plus the approximation of y prime in tj plus 1. And this actually means that our approximation of y prime, or not y prime, actually this is more like our approximation of delta y from tj to tj plus 1. So our approximation of the change in the function y from tj to tj plus 1, the approximation of the change that there is based on an average of the derivative in the time point tj and the derivative in the time point tj plus 1. So it seems like some kind of combination of Euler, forward Euler and backward Euler, and intuitively it sort of makes sense for us. So now we have just a little bit more understanding about what this Tripetz method is about. So let us try to construct this method. Constructing the Tripetz method by using the Taylor approach. So what do we mean by the Taylor approach? Well, the Taylor approach, more or less, is just this method we use to construct finite difference methods, where we approximate values of y prime, etc., in points that are close to a point where we already know a lot about y. So by using the Taylor approach, what we want to do is approximate, for example, y of tj plus 1 and y prime of tj plus 1 by using Taylor expansions. And now recall the definition of tj plus 1 in terms of step sizes. We mean by tj plus 1 the time point that is step size k away from tj. So let us try to do these two Taylor approximations here. So the first one, I want to approximate y of tj plus k by doing a Taylor expansion around the point tj. So by Taylor's theorem with Lagrange remainder, I get that y of tj plus k is equal to y of tj plus y prime of tj times k plus y double prime of tj times k squared plus y triple prime And here I think that we've got enough terms that I can do the remainder term now, times eta 1 times k third divided by 3 factorial, which is 6. And here I have a 2. Okay, so now I have this expression here. And before I just go on and mindlessly Taylor approximate y prime of tj plus 1, let's try to look at how much this expression reminds us of what we want to end up with. Well, we want to end up with something that involves y of tj plus k and y of tj. So this part is golden. And now I have something with y prime of tj corresponding to fj up here. And I need to be able to plug something in here that allows me to have an expression that involves y prime of tj plus 1. So that might suggest that I will need to isolate y prime prime of tj in the Taylor expansion that I used to evaluate y prime of tj plus 1. So let us try to take a look at that. Y prime of tj plus k is equal to y prime of tj plus y double prime of tj times k plus y triple prime of, well, now I also think that I'm far enough along in my calculations that I can involve my remainder term here, and let's just call this eta 2 instead, multiplied by k squared halves. Okay, so what I want to do is I want to isolate y double prime here, isolate apparently. So I have that y double prime of tj is equal to y prime of tj plus k minus y prime of tj divided by k. And then I have another term which is y triple prime of eta 2 multiplied by k squared halves divided by k, which is multiplied by k halves here. Okay, so what do I do now? Well, now I go on to my next step, which is to say that I want to plug y prime of tj back into the expression that involves y of tj plus k. So y of tj plus k is equal to y of tj plus y prime of tj times k plus, now I plug this expression in, and I have k halves, k squared halves divided by k, that's k halves, multiplied by y prime of tj plus k minus y prime of tj. And then I have minus y triple prime of eta 2 multiplied by k to the third divided by 2. And I add y triple prime of eta 1 multiplied by k to the third divided by 6. Okay, so here I can move this into the parentheses, and what I have is y of tj plus k halves multiplied by y prime of tj plus k minus y prime of tj plus y of tj, y prime of tj, so that's actually like this. And then I have some expression that I will here say is the same order of magnitude as k to the third. Now, the funny thing is, if we look at table 1.3 on page 16, then beside the finite difference formula for the trapezoid rule, they actually say for the trapezoidal formula, they say that the truncation error tau j is equal to, well, it has the same order of magnitude as k squared. But why do we have a truncation term that's k third then? Well, the thing is that in the book, there are some rather different ways of attacking, well, what do we mean by truncation error? Well, let's just first establish that now, if I just remove the truncation term over here, then I have actually ended up with my trapezoidal method. So we're already home safe. We have what we need now. But the thing that's bugging us is that the truncation term we have here has the same order of magnitude as k to the third, whereas in the book it says that it has at most the same order of magnitude as k to the second. So I would like to talk a little bit more about this in the next video, where we will be talking about local error and global truncation error and truncation terms and when the book uses which. So let's talk about that in the next video.